This video is really a continuation of carbon-13 NMR. We're going to be looking at DEPT NMR, and that stands for distortionless enhancement by polarization transfer. What that kind of means is that the signals from carbon are enhanced by transferring magnetization, basically, from the protons, which are much more abundant and visible in the NMR. So you get the coupling information that we talked about in the last video as being hidden information in decoupled C13 NMR. This will enable us to identify and distinguish, more importantly, methyls, methylenes, and methine carbons. The depth spectrum will show often carbons that are methynes and methyls pointing up, while methylenes are pointing down. But there's a very varied ways of doing this. The best thing to do is to look at an example in depth. So this is the molecule ipsenol. I've drawn it over here on the right so that we can see all the carbons and protons. On the bottom is the regular carbon-13 NMR spectrum. The middle is the most useful. That's our depth that we do most often, where the carbons that are CHs and CH3s are pointing up, CH2s pointing down. And then you can distinguish the CH3s from the CHs by doing one more depth where it only shows the CHs pointing up. The other thing to point out is that quaternary carbons, which are not CHs, CH2s, or CH3s, are only in the carbon-13 NMR spectrum, and we can actually spot one right away right there. The farthest downfield signal must be a quaternary, since it doesn't appear in the depth. Any other quaternaries? No. The other thing to see is that solvents appear in regular carbon-13 NMR spectrum, but typically not in the depth. Sometimes you see a little bit there. All right, so looking at the molecule, we can divide it up into groups. Where are the CH3s, for example? Here and here. They're equivalent, and they're going to be pretty much upfield. We see three signals here, far upfield, one of which is a CH. The other two must be methyls then, because they're not CH2s pointing down. So these two signals are due to methyls. And how many methyls do we have in the molecule? 2. So there's C1 methyls. We don't know which one's which we'll get back to things like that. Now we have how many CH2 groups? 1, 2, 3, 4 CH2 groups. We have 1, 2, 3, 4 CH2s, methylenes. Look how much more deshielded these are. Those must be 8 and 9. I'm calling this 9. Because they're alkenes. So the chemical shift values are still here, right? Still usable. Again, we don't know which one's which, but we're looking at C8 and C9 there. So the other two methylenes are 3 and 5. They're both on either side of this alcohol, so that doesn't really help. 5 is closer to alkene. That might deshield carbon 5 a little more. If you had to guess, you might say C5 and C3. But again, that's pretty much hand-waving and not direct evidence, right? Okay, so it should already be unsatisfying, even though we're looking at more information, that we can't nail everything down perfectly. And that's really the goal of this class, actually. More and more sophisticated techniques in order to distinguish, for example, C5 from C3, C8 from C9, and the 2 methyls at C1. Now, what else do we have in the spectrum? Methynes, CH, CH, that's 2 of them, 3 of them. Okay, so the methynes, let me go to a different color. 1, 2, 3 methynes, broadly spaced. This one should be easy to spot since it's so deshielded. That is C7, right? Because it's an alkene methine. C7 for sure. The other 2, the next most deshielded one should be C4. If you look at C4, it's next to an alcohol. In fact, it's on the same carbon as an alcohol, so it's going to be much more deshielded than C2, which is sort of just your regular alkyl methine, CH. So those are assignable without much ambiguity, really. What is left unassigned? Is there anything? I guess that's it. The quaternary is where? Right there. That's quaternary carbon, C6. Yep. And I think that's about it. So at least it's easily seen that DEPT can really help assign a lot more atoms than we had been able to previously. And it makes use of the coupling information, the quote-unquote hidden coupling information in carbon NMR. So we're actually going to look at more advanced techniques, this same molecule, ipsenol, and see how those techniques allow us to distinguish everything for sure. I'm about to send out homework 1. That'll be a graded assignment. I think with the schedule now, the syllabus should be out soon. And then keep working all those spectroscopy practice problems that were posted on Canvas. The answers are now posted as well. And if there's a groundswell of requests for more such problems, I do have more. But we really need to move on to new topics too. So, okay. Keep at it and see you at the Zoom meeting.